This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. Thanks for coming along.
Richard Hammond gave us a little demonstration about a column of the slot in it last time, and I was moving into a little bit of the underlying theory. I got to this point saying an inverse square relationship for long columns. And the next concept, that idea of unitless effective length, comes into play. And this is just one of those nuances associated with how the member, the B, in this case column, is fixed at its end. Little icon top right hand corner, it looks like it's got fixed ends, but you can still see the column bending as if it was just between my hands, flat, as if it was rotating on a pin joint. So we've got this idea of effective length compared to actual length with a ratio which we happen to call M of actual length to effective length. Question? Thank you very much.
Shall I start again? I might. Thank you for that. Mike's not on at all. For the people at home, I just got started on effective length. So we've got this ratio. Lowercase m is what people tend to use for the equivalence. And here's some values. And for me, the fun one is the top one. The idea of, hey, just as an aside, and I say this a bit, what's great about the stuff I teach you about is you're in the lecture and you forget this stuff and you're allowed to take a ruler in. All you've got to do is that and think, okay, the top one, I've got a pin joint, top left-hand corner, fixed free corresponds to fixed end at one side, free at the other, and we get that kind of effect. Pin joint, just the standard, fixed, pinned, we get a different kind of effect. Second from the bottom, fixed, different kind of effect again. Now you have a little ruler in front of you, you'll be able to you can just play with those ideas, and it helps with the intuition as to, are you assuming the correct end fixation, thus are you choosing the correct theoretical value for m between actual and effective length, moving forward into the equations. So fixed free is a nice one. It's like a mirror image cut in half. And the free end implies that end, the fixed end of the column, doesn't have to be in the same horizontal line as the free end. Now for all the others, that's not true. That they are all in the same line of action. And of course, the stronger the end fixation, or the more secure, less freedom, we're going to have this column down the bottom in particular with m equals 2. That's going to translate to a column that can cope with a lot more load before it's going to fail, according to elastic deflection, the Euler approach. So pin 1, free fixed, 0.5, fixed pinned a bit more odd, about 0.7, and fixed too. Now, I often talk about changes over time, that engineering, there is a lot of uncertainty and you've got to be careful of your references. So here is a lot of material coming out of the Budniss textbook, or Budniss and Nisbet textbook, and we've got same essential process. We've got a whole heap of far prettier images here, by the way, but I'm not expecting you to read it all. Have a look at the book. But we've got fixed free, rounded rounded, fixed rounded, fixed fixed. The second one is rounded rounded, and it's all the unities, as per what I was saying, so pin joints at either end. Fixed free, we've got a quarter up there. So a quarter compared to a half. Well, how does this value C fit into the equation is something to contemplate as well. Fixed rounded, where are we? Fixed and rounded is 2. And let me make sure I'm right on this one. ABC, there's the quarter. Fixed rounded, there's the C equals 4. And fixed is not even shown, is recommended value of 1.2. So 1.2 for fixed and fixed rounded. Rounded obviously means pin joint. So the values are quite different in these recommended value realm compared to what I've got here for M, but we've got to remember that M and how we introduce M into these equations, one versus another, does become interesting, because after all, M is affecting L directly here, and L is squared, so 0.5 squared corresponds to 0.25, so that's fine. We go, oh, sorry, wrong way. We go down to the fixed of 2. Are we going to get a 4? Well, no. But fixed is 4, so that's okay. This one, they've also got as, sorry, I made a mistake. This is fixed because the rollers only go in and out. If it was held perfectly at either end, we'd have a whole heap of other complications of stretching going on, in addition to just the basic distortion, the Euler distortion. So that is actually a more precise representation of what's going on than what is down here at the bottom. Okay? So in the end, despite the first view of seeing things a bit different, they are actually quite similar. However, we get to these recommended values, asterisks, and it says there, to be used only with the liberal factor of safety when the column load is accurately known. So the idea is you can use that value, but liberal, that means a lot of, a high factor of safety or factor of uncertainty. So your textbook is telling you, yeah, there's still some uncertainties here. It's not perfectly understood. So, just approach with caution. And I'll just repeat the most important thing about, oh, I'm sorry, something got lost. I was checking this before too. Pi squared, I'm sorry. That should be a pi up there, which has gotten lost on each of those images. I'll just even write that down so I don't forget. I'm sorry. So, I think that's enough on that. That's another argument. In infrastructure engineering or civil engineering, that idea of fully fixed end, even in our world of a pin joint, the idea of a pin joint is it's zero friction, infinitely rotatable, and of course that's not true. There will always be a bit of friction. To have something fully fixed implies that how this column in this case fixes into that end support is perfect in that it's always going to be coming normal, coming out, in this case, normal to the surface without any wobble, without any chance under load of one object distorting the other object and vice versa. And of course that's not true in practice. Thus, these kinds of recognitions of that inaccuracy. In my world, if there's a, my world means your world, we will deal with, I'll go back one so we make sure it's really clear, we'll be dealing with this equation. And we'll be dealing with that, italicised L. That is the effective length. Just in case, I will not replicate that information in an exam setting. I will only provide the earlier slide. Just make life a bit easier for you. You don't have to sort of overthink it. Just be aware that different references have slightly different ways of representing stuff. Okay, radius of gyration now. And this has got everything to do with right down the bottom. Cross-sectional area is a property, millimetres squared. Second moment of area, different property completely, millimetres to the power 4. And what I want you to just be aware of is this idea of how much material is how far away from the neutral axis has a big bearing on how a column is likely to distort or to deflect. And here's just a simple little example. Both section number 1 and section number 2, the idea is they've got the same sectional area. One on the left is a rectangular, solid, pretty much like the ruler that I'm waving around. The one on the right is a very goofy looking I-beam. Long horizontal sections and a very slim tapered section between them to hold them together. Now, equivalent sections, equivalent areas, and in this case, it's been designed in such a way that IZZ for 1 corresponds to IZZ for 2. This has to, you have to do a lot of playing around to make sure that the material out here, the extreme fibre, is equivalent to all the material performance of the extreme fibres of these column top and bottom. But of course, we've got something like that, and we're going to want to put it as use it as a column. And again, I've just talked about the way in which that column has its end fixation will have an impact on how it distorts and which way it's going to want to distort the most in terms of long columns and deflecting. They will have, you can see just by looking, we've got a very different second moment of area in the IYY direction between the pair of them. And by analogy to the ruler, again, that I'm waving around, it only ever wants to elastically deform in one direction. It never, it never deforms towards you or towards the board because the second moment of area is so much higher in that direction, as per that radius of gyration. Same essential process. So that leads on to something like this. As a designer's issue, we've got the same component, we've got a component. I'm not going to say it's a component, it's a beam, solid, rectangular, and it's got this funny little, slot that it's going in between. It's got an axial load, and then the question is, how do we determine the direction in which this column will buckle first? Now, I hope everyone in the room is already able to see what's going on, but if not, that's okay. I will first look down on that object from above and do my best to do a sketch. Okay, we've got our loads applied. We've got that wall in the middle. We're just with reference to what's going on up there. I've got that wrong. Z is parallel, and X, we'll put it going that way. Hopefully everyone's already seen what's going on with this. This, what I've just sketched, is the thinner section, the lower second moment of area projected section view, but we've got this funny looking thing in the middle. Now let's idealise it a bit, as if it was a double-sided pin joint. There's nothing, no, without any further information. It could even be solid. You know, it could be theoretically. But very close fit. Still clearance. Then it would be, you know, that argument I put before about really hard to get a perfect fixed end, or very hard to get a very perfect pin joint. This object cannot just rotate. The blue cannot easily rotate in the realm of that slot. It can wobble a bit, it'd rattle, but it'd get to a certain point and then it would be fixed, as in fixed end. But let's not worry about that for now. Let's just think about it as being a pin joint. At the end, there's no more information about how, you know, those free ends of the main beam are being supported. Let's just imagine it's a pin joint for now. And we could expect something like this. Okay? With what I did there with a pin joint, we expect that central zone to not move anywhere. So we've essentially resisted or limited the amount of lateral deflection, Euler style, that beam can travel in that direction. If we had something like that, it gets harder for me to sketch, we would expect a very slight, you know, tiniest of slope to accommodate the imperfection of the fit, but still we would have the same kind of effect. And that zone, of course, is where it's most important to think about. But still, one way or another, we would expect to have that kind of wave pattern. I hope everyone knows where I'm going. I will lift this a bit. And let's hope. Now, as far as we're concerned in the view that I can't see anymore, x, y, as far as we're concerned in this direction, I'll put them all down in a sec. Now all we're going to have is the standard, you know, effective length 1 compared to a different effective length. This, you know, a question like this in an exam setting without any further information, the best you could do is what I've just talked about. You cannot with certainty state that this is going to fail first or that that's going to fail first, because there's conflicting, you know, issues at play. If the beam was rotated 90 degrees and then this section was actually between the pin joints, life becomes a lot easier. It's very, very easy to predict which way it's going to fail first. But something like this is a, you know, I have asked a question of this ilk in the exam in the past. Just if you want to write it down, but not often. Let's move on. Long columns have been, you know, there's an equation, there's some issues associated with effective length, how is it being fixed at its ends, are there any intermediate limitations to just free Euler fail by deflection motion. Now, onto short and intermediate columns, because that earlier chart I had just had a big question mark in that zone. What happens when the ratio of L on R, effective length on radius of gyration, goes towards 0? Well, we get closer to this idea of yielding. Very thing up there. So we could conceivably just have a horizontal line at SY, capital S for yield, and and just put a horizontal line across. But it's not as simple as that. You know, of course, yield point is going to be a limit for ductile materials, for ongoing elastic behaviour. But as soon as we move out a little bit from that, L on R equals 0 point, we can expect something else to happen. And people who have read ahead will know that people have put a lot of methods out there, but the Johnson parabola is the one that we'll worry about in this class. So instead of all the words, you can read that in your own time. There it is there shown in small scale, and there is the essential equation associated with it. That's got to be gee whiz. I checked all this before I came to. That's L on R, comma P on A, it's like X, comma Y. It's like a 1. And corresponds to yield on 2 is the y-intercept, and this equation associated with yield as we move down to the so this point here, by the way, 2 pi squared E on yield strength, SY on 2, and that's what we regard as the point at which we transition from the Euler long column formulation to the Johnson, dare I say, short column formulation. And in very small text is the overall equation. I'll move ahead one, you can see it a bit better. So the critical area on, the critical strength, the critical load associated with a particular column with a section area A can correspond to this equation as far as the Johnson formulation is concerned, with yield strength corresponding to the upper limit when we've completely at a very, very, dare I say, infinitely thick, infinitely stumpy column. What else is worth talking about? FD has been included there for design factor of safety, and FD has been included in the Euler formulation as well for design factor of safety, as you might expect. We have lots of uncertainty. Now, as far as you're concerned, it's a parabola. It's symmetric about the y-axis. It's got a heap of stuff associated with it. Young's modulus has to be there. Effective length has to be there. No wonder I was talking about that. The R is still very present. L on R. Pi squared, nothing else. So it's now that you've got this as an idea, everything else is just playing around with symbols and numbers to come up with solutions. This is a critical thing that I have played around with in exam settings, the transitional slenderness ratio. Now, you might be given a problem where you've got loads and length and some parameters, and you've got to then finish the design. You can't finish the design really until, let's say after a geometric factor. You don't know whether it's Euler or Johnson because you don't have the geometry yet. So the best you can do sometimes is make a best guess. Can it cope, can whatever it is cope with a certain quantity being put into an equation? Do a check, find out is it Euler or Johnson? And one simple way is, have you got enough information to check to see whether L on R is greater than or less than that particular value? That helps you on your way. Because otherwise, you're just lost. Which equation do I use? So, as I said before, introduce a design factor of safety is always very good. P on A for design, P critical on A for area, with multiplied by 1 on FD. And safe always means less than or equal to. We want to be in the safe region. I'll go back a slide, back another, no, I haven't got it yet. We've always got to be within the safe zone. The closer in that little safe zone we get to the x-axis, we're safe, but we're over-designed. It's bigger than it needs to be. The closer we get to this limiting curve, the closer we are to optimising, but then we don't necessarily have much extra performance available should some person or some system try to go outside of what we'd call the specification for the column. So the idea of stay within that zone is safe, be up in this region optimising the design for performance, but you'd have to be very clear in the design specification that we have optimised and there is no, the design factor of safety has been applied and we're right on the limit with whatever design you've chosen. Recognising that even with what I've got up there, yield strength, and you've got yield strength divided by a factor. I can tell you it's not 2, it's probably about, design factor of safety is about 1.5, I'd imagine, something of that ilk. Design factor of safety of 2 would bring us down to this halfway point, and then we'd have another curve going along there. Sorry, just checking to see if the pi, yep, the pi works out. That's all good. So now, that's it. A couple of equations, a curve that has, 2 distinct equations associated with 2 distinct theories, where Johnson's more about crushing, Euler is about lateral deflection. And what's up on the screen now is a bit grey, I'm going to zoom it in a sec, of the algorithms associated with column design. You might remember at the start of this lecture, I had a little flow chart of axial tension. So here's a CASO, designed for geometry. I talked about just a moment ago. Imagine that the dependent variable is associated with the size of the object. That means that you're after geometry, area, radius of gyration, and you might be given the material properties, Young's modulus, strength, the length, maybe even how it's been fixed, what load we have to cope with. You might have to come up with the design factor of safety, but one way or another it has to be there. And the rest of this is a process. Now, at this point, this is where I said before, you make a guess. You assume long column, guess the dimensions, then have a look at the inequality and see if it's working out for you. If it is a long column, great, the solution's okay. If it's not a long column, well then you have to go with the short column formulation, do another check, solution okay for short column. If no, you've got to go back, increase the area, increase the radius of gyration, or both, to be able to cope with a solution that's okay for the size we're looking at. Because let's not forget, the loading and the distance apart from where those loads are applied, plus the way the end fixation's occurring, all that is feeding into what you need to have in terms of area and radius of gyration. So it could be that you're thinking it's going to be nice and slim, but you actually need something a lot fatter for the material you've got. And it's so sort of bulky, in fact, that it becomes a short column. That's just, it's got 2 decision points in this particular formulation. And of course, I'll go back. In fact, you don't have to assume long column. You could assume short column. This is just a flow chart, not the one and only flow chart. Now, for this one, second case, this time we think we've got everything else is given. The material is provided, make sure I've got it right, all the geometry is fine. That's all given. And we're after what's the maximum load we can cope with. And that's what it's down there, designing for maximum load. We have got enough information now that we can actually check our transitional slenderness ratio against one or the other columns. Yes, it's long. No, it's short. And as soon as we're at that point, we can complete our force calculation for critical. And then we can say that our allowable force has got to be at no greater than a critical load divided by our factor of safety. Hopefully everyone in the room can see why I paused and gave a few more words about the design project or the design question that seeks a geometry answer. Just by the complexity and the number of stages of this flow chart, it's a bit harder compared to this flow chart. when we've got everything but force and we're just looking for force. Now, mud maps or concept maps. What's on the screen now is, because this is, column design is not meant to be hard. Spring design's got a fair bit more stuff in it. Column design, you've seen the equations, there's a bit more to come, but by and large, there's a bite-sized number of variables to deal with. And how they all impact on the overall design process can allow a concept map or a mud map of the style that I put up on the screen. It's not that bad. And by way of another hint, those students who are wondering, let's say you didn't do mechanical design with me, but you've come in laterally, what's up on the screen, do your own form of this, is a very nice way of getting the ideas in your head, preparing for exams and preparing for your learning of this material. It also helps when, if you bother to buy the Budness and Nisbet book. I don't cover every machine element design component or style, and there's a whole heap of little nuances that the thicker, newer editions keep pumping out. And that's part of the process. Where do these things fit in? What's similar, what's different? I'm just trying to give you the, be aware. If something looks wrong, then check. Check the references. So this bit here is important. There is no one correct map. Whatever works for you is what you should use. Now, because you've all seen this, it's probably it'll be a bit harder to come up with something that's your own. But I didn't do this for springs, the first topic, so you could go back and have a go at that if you feel motivated to do some homework on this. Now, by way of fun, I'm a big fan of concept maps. You might remember from the very first lecture, I built up to Bruce Field's complex map for mechanical design with all the little bubbles that correspond to areas of interest, not even any links in it. And I indicate which of the topics therein I cover in this particular lecture. I'm going to do it again, this subject. I do the same thing for design for integration next semester. Thus, I think it's a useful tool for representing complex information. Now, while I was saying all that, hopefully you were reading this. This was during Gulf War II, 2010, in Afghanistan, and General Stanley McChrystal was quoted as saying, "When we understand that slide, we'll have won the war." Boom. That's the slide. Thanks for laughing. That's the slide that he was presented with. What a joke. I'm pleased that you laughed. It's worthy of being laughed at. You're thinking, why? And then you could ask yourself, who was the person that said, "Oh, we'll have to do a concept map because then we'll understand what's going on"? I'm at a loss to understand the thinking that would go behind something like that. So, look, if you can be bothered later on and want to dive in a bit, you'll pick up that some of the concepts therein are actually of merit. You have to unpack them in terms of what do you mean by that little phrase, but then to have so many cross connections, it just as I'm going to go back a slide, as it said, a sprawling spaghetti diagram. Now, stuff like this undermines the power of stuff like mud maps or concept maps. Someone's taken it too far, to the point where it's unworkable. Now, maybe, I don't know, someone with Asperger's is talking to someone else with Asperger's. They might both understand it completely. But then what do you do with that information? How do you communicate it to other people to get outcomes? How do you, like that general said, "I've got no clue what's going on here." It doesn't help. It doesn't help solve the problem. So, back we go, to stuff like this, I say, yay, it does help solve the problem. Any tool will have its limitations, but this one did not. Let's move on. There's a little bit more to go. Mechanics of solids texts go on with to a bit more detail than what I've done here and what I plan to do here for design. What about when we've got an off-centre load? We've got an eccentric. The eccentric itself will introduce a bending And it is a potential variable. It speaks to that idea I said about fixation, and usually it is the end fixings that provide the loads as well. And if we don't have a uniform load, top and bottom, well, where the load itself is starting to provide a long column failure mode. A second imperfection could be that the column, even before it's loaded, has got an outer straightness. It's already got a bit of a banana in its form, so it's sort of it's been prepped to start distorting. So these eccentricities, I'm not going to talk about in depth, but they are something to think about. Now, when the secant formula is introduced, and it talks, it's just getting into that idea of when we've got these eccentricity errors. If everything's perfect, well then the Euler and, if we like, the Johnson formulation is fantastic. But you can see the family of curves going down as eccentricity E increases. It's another way of saying factor of safety. We can't trust that the column is perfectly straight. We can't trust that the forces are acting along the neutral axis, so we add a factor of safety. This is a formulation that, acknowledges in a quantitative, theoretical way that we have an eccentricity, and what do we get as a consequence of that? And you might note that and this is stuff I pulled out of other resources. When this secant formula is used, they just presume yield strength failure until we get to the Euler curve. So there's a bit of uncertainty about the zone where the laser's waving now. Is the Johnson formulation better or worse? Where's the uncertainties? Et cetera, et cetera. Now, many modern, dare I say, civil engineering codes or standards make use of this secant formula. And here is an example of an Australian standard, one's from 81, then it was 1993. There's a strut, another word for column, as far as we're concerned. And there's a whole heap of equations for axial stress in uncased struts. And there's this rather nice little phrase there, which I'll zoom in so you can see it all. When you've got an imperfect column, that is an outer straightness column, we've got this eta, dimensionless outer straightness parameter that corresponds to this outrageous number times effective length on radius of gyration squared, and it's established by some clever dudes, which, is part of their formulation up here, which is a bit more complex than the one I've given because they've added in factors. One last thing. We've got, it's not for everything, but John Weir, Bruce Field and myself. Now, you'll meet John in a couple of weeks. You'll meet Bruce next semester. Developed something called SimLed. It's, we never got it to a commercial level. It's a beta level design tool, and it's on all Melbourne School of Engineering PCs. It's getting a bit old now, but anywho, it is what it is. Simulation modules for learning and engineering design, and we do have a very nice columns module. On the left-hand side, it's essentially the responder window or half. On the right-hand side, it's the controller half, a series of tabs, and you can play around with everything. Because of that mud map style, we've tried to map the mud map onto a tool so that students, like yourselves, can play around. We thought of it as electronic clay. You can play around with proportions and to see what effect that play has on, if you can't really see it well, but there's a green little half arrow and a red little half arrow, so that when we've got asymmetric systems with non-symmetric end fixation, they move apart, and it helps with that idea of in which way is a column going to fail. Red implies fail, green implies not fail. It's within that bound. So, and there's a series of standard shapes, etc., that you can play around with. So, again, those who want to review material, gain a deeper understanding, there's a tool that you can make use of. And as far as columns are concerned, we're done. So allow me to pull up another. I'm sorry that PowerPoint had a few glitches in it. So I'll make a start for the 10 minutes I've got left on another design feature. Look, they call it machine element. The idea of an object that either contains pressure or contains vacuum, and that we, the engineer, is expected to be able to quantitatively design and ensure safety. Now, pressure vessel design is safety critical, and so there's a fair bit of stuff to get through. I won't get through it all today. I'll be focusing on internal pressure, and I'll be giving you a bit of, there'll be a couple of case studies, as there always are. If a pressure vessel fails, especially a pressure vessel that contains gas, it is, catastrophic, invariably. Often steel, mostly steel, we get the release of that gas at a sonic velocity. So the steel will just peel away, the vessel can easily turn into a rocket, and if we've got heat plus release of gas, there's something called BLEVE, which I'll talk about later. It's essentially an explosion plus rocket, and very, very serious consequences. So, design of pressure vessels is has to be done in a very conservative way. And Peter McGowan talked a little bit about that when he was here, but people don't get there's no authorship in the vessel Australian standards, but Peter McGowan pretty much wrote the current vessel Australian standard. So again, homework, if you want to have a look, go and have a look. So pressure-induced stresses, design equation, and to make it a bit more fun, this part's super easy, but let's try and complicate it a bit by introducing pressure with an associated set of forces that a real-world vessel would be expected to have to cope with. So hopefully everyone's seen vessels around the place. These kinds of bullet-like vessels on two stirrups. Gas is often stored that way at petrol stations. In plants, chemical plants and the like, they'll often have these kinds of vessels where essentially the domes are mounted on a vertical axis compared to a horizontal axis. One more thing to note on this, I said domes. It'd be, for a pressurised system, you would never put a flat plate on the end. The flat plate would want to bend, distort, bow out, and you put extraordinary stresses on that region of discontinuity between the cylinder and the end plate. That's why there's this doming. It's the stress levels in that interface or in that discontinuity zone are high enough as they are. I'll talk about that later. So it'd be just, you can see, it's just a norm that people make use of. Again, later on, I'll be talking a bit about these things called flanges. Flanges are a nice way to have a pipe-based pressure vessel, in this case. Just because it's a pipe doesn't mean it's not also containing pressure. But if we've got a piping system and we want to be able to disassemble it readily, we'll have something like this, a flange with a series of holes in it. We put a gasket, a soft material, where I'm waving the laser now, then put the flange of the next component against it. We hope all the holes line up and we bolt it all together and provide a friction grip that distorts that gasket a little bit to stop routes, pathways for which the pressure can escape. So, but nonetheless, just because it's a pipe doesn't mean it's not also a pressure vessel with all the associated weaknesses at these discontinuities that you might expect. Have another look at this one. This saddle point, what's nice about it, it's providing a nice, extensive region of contact, reducing the contact or Hertzian stresses around that vessel. However, that also is, if you think about that vessel, it is essentially a uniformly distributed load with two reaction points, one there and one there. So, it's going to want to bend in the middle, like a beam would bend. It just so happens that this beam has a hollow circular section. And there's a close-up, by the by, of the flange. Series of bolts, nuts and bolts around the outside, have to be assembled, put together. Squeezes the joint in a way that pressure can be maintained or contained within the pipeway. And there's some nice issues associated with different failure modes of a system such as that. Now, just to keep you all, keep your thinking broad. The heart and even the blood vessels, arteries and veins, are pressure vessels. The heart is a pump as well as a pressure vessel, so has its own performance nuances. One of the wonderful things about a heart is that it has to have minimal turbulence. We can't have eddies zipping around because otherwise the blood loses its properties. Various elements of, because blood is not a liquid, it's a slurry. A slurry of a variety of things, and we can't afford to have any of that slurry just sitting around, in a dwell state, in a static state. The whole lot's got to be continually moving. Thus, a very interesting style of pressure pump. And slurried pump design is an interesting area in itself. Simple stuff that hopefully everyone's seen. Coca-Cola, spray cans of various kinds. They are pressure vessels. They are low pressure vessels. And also the pressure of the carbon dioxide can leach out over time because of the thin wall of the polymer. But nonetheless, pressure vessels they are. Bike pumps are another. They're also low pressure. We're not going to kill ourselves if one of those things ruptures, but they are still pressure vessels. And great, I've got enough time to finish this off. Where did I put it? There's little point me asking what this is because it's up on the screen. Hope it doesn't roll off while I go over here. Okay. Try that one. Over we go. Screws on, screws off. Cap. There is a very thick bit of injection moulding. Hopefully you can see there's quite a lot of material in there. It looks a little bit like a vessel you'd find in a laboratory, but it's not. That object is this object up here. It's like a preliminary manufactured component that will later be turned into a final, if you like, carbonated bottle associated with stuff we go and buy at the supermarket. It's called a preform. It's used because it's cheap, simple to manufacture. That preform that I just was waving around essentially is there. Now, under heat and pressure, blow it up like a balloon. We've got an outside. It's within a die. It is what it is. It's a die, so that as the balloon of that heated up preform expands, it gets limited in its growth by the form of the die. And of course, this is in mega fast production systems. That's why we've got this stop animation process going on there. I'm not going to read all that stuff. You can have a read yourself, but it's usually from PET, polyethylene, I can't even say it, terephthalate, and there's all sorts of other interesting things. Carbonated beverages, 3 to 4 atmospheric pressures, and the wall thickness is difficult to control. And I'm going to show you a video to finish off today, and my friend David Downing, who's a doctor, finished his PhD here, he was working for Amcor, of all things, and okay, these bottles contain carbonated water really well, they do that nicely, but there was an associated design requirement that those bottles had to have enough structural, in this case column type strength, to be able to support themselves in pallets. Now these are boxes and boxes loaded on a pallet, then another series loaded on a pallet, and we got that lean. Now, I don't have this bottle because, of course, they had to reject, but they made the bottle so thin that they started collapsing in on themselves. And I've got a video that I'll show you, and then I'll stop. And this is the sort of stuff that's available. So this is David's own bit of, make sure I get the software right. It was either Abacus or ANSYS, very highly nonlinear application. And so David spent a lot of time trying to optimise these things for thickness so that they could still accommodate load. I'll show you the other one that he provided me with. Abacus is the software. So this is the sort of stuff you might think, you know, what is there available for a mechanical engineer? Is this associated with mechanical engineering? Absolutely yes. You know, trying to optimise, reduce material, material waste, material use for every item that we produce, you can see what's going on up there. Not enough material in that zone that would otherwise be near where the threaded zone has been introduced. And there was red zone means failure, problem, got to be redesigned. And of course things were redesigned. And that's the whole point of, dare I say, the profession that we're in. Even when we, oh, sorry, wrong. Don't quite know what's going on there. Oh, no, it's okay, it's a static. That's what I wanted to get to. That these sorts of problems can be unexpected. You know, I wouldn't be surprised if when Dave was doing this, he thought, oh, they'll never have more than X kilograms worth of weight on a bottle. The bottle's sitting right down there, bottom corner. But no, someone decided to stack them up twice as high, if not 3 times as high, thinking it looks pretty solid to me. But this is what can go wrong. And it does. And engineering means engineers should always think not a problem, but an opportunity to learn a bit more and delve a bit more deeply into why we had this unexpected failure mode in what should have been the focus of this should have just been the failure mode of pressure vessel. That'll do. It's time for you to go. Thanks for coming, and I'll see you next time.